Hello, my name is Corona Vadaria. I am from Yekaterinburg. My project is changing the oscillation period of the conductive sphere in the magnetic field. Magnetic field can variously affect the moving conductive bodies. The effect of the magnetic braking is widespread in technology. In particular, it's used in railroads or maglevs. If the motion process is periodic, magnetic braking can change not only the speed but also the period. This phenomenon is the focus of our research. For example, a light conductive sphere suspended on a thin wire and oscillating torsionally is braked and stopped when it enters a magnetic field. The aim of our study was to investigate the influence of the distance to the magnet, the thickness of the foil layer, its material, and the magnitude of the magnetic field on the oscillation period and damping coefficient of the sphere. A cellulose tennis ball covered with aluminum foil was used as a sphere. It was suspended on a thin copper wire. Here we can see oscillations of the sphere without a magnetic field. And here we see oscillations with a magnetic field. We can see that when the magnet appears, the sphere slows down and stops. Let's understand why this happens. Without a magnetic field, we see damped oscillations, but they damp down quite slowly because of energy loss from twisting the wire and air resistance. When the sphere is placed in a magnetic field, the magnetic flux begins to change through an arbitrarily chosen circuit of the sphere. According to Faraday's law of electromagnetic induction, this change in magnetic flux begins to create an EMF in the sphere space that is equal in module to the rate of magnetic flux change. According to Lenz's rule, the induction current in the sphere caused by this EMF is directed so that the magnetic field it creates prevents the magnetic flux from changing. This means that if we look at the sphere from above, a field must be created at the point approaching at a magnet, whose magnetic induction vector is co-directed with the magnetic induction vector of the magnet. At a point away from the magnetic induction vector is opposite to the magnetic induction vector of the magnet. The approaching point tends to push away from the magnet, and the outgoing point tends to attract to the magnet. Both forces create a torque that inhibits the rotation of the sphere. First of all, we investigated the effect of the distance between the sphere and the magnet of the period of oscillation and the damping coefficient. We put them at a distance of 4 mm and 10 mm. The greater the distance to the magnet is, the smaller the damping coefficient and the period of oscillations are. After that, we changed the thickness of foil. The greater the thickness of the foil is, the greater the coefficient of damping and period of oscillation are. We investigated the effect of the material of the foil. A ball roped into the copper foil stops earlier than the ball roped into the aluminum foil. We change the magnitude of the magnetic field. The greater the magnitude of the magnetic field is, the greater the coefficient of damping and period of oscillations are. Our experiments show that the greater the distance of the magnet is, the smaller the damping coefficient and the period of oscillations are. The greater the thickness of the foil and the magnitude of the magnetic field are, the greater the coefficient of damping and period of oscillations are. The material of the foil affects the period of oscillation and the damping coefficient.